let's continue for the second programming challenge. We will draw our, it's not easy to pronounce, it's Sierpinski triangle within this chapter 6. So we will draw this. It's actually our fractal. In Chinese, it's called Sierpinski 三角形. So it's like this way. So you can see the most outside is a triangle, and then they just repeat is this triangle include the three same, just the half length, half edge length triangle, and every triangle has the same the inside. So then is half. So we just repeat that. Then this result will be putting like our book is like this. So let me see here. Our book is if we have 10,000 times or points, it will be very busy like this. So that is an interesting thing. Is but even you saw that is quite complex. But if you read from our the mind map, actually, what we have done using this bind-slave friend can do this drawing directly, because let's recap is if you want to make our fractal, and now is we have the equally or uniform the probability. Then what are the key things you need to do? So 3 parts. Let's remember again. So first is the starting point or the initial state or initial shape with the position. Second is the numbers of the repetitive numbers. So that can decide your fractal's iteration, the numbers. And the last is the key for your fractal is the transformation rules. If we use the rules to fit in the bind-slave form, then you draw this bind-slave form. The like is those structure, and now is we can just use the same logic and convert or change the transformation law to this Sierpinski's triangle. Then this we will use new rule to draw the new the fractal. So that is the high level the ideas, and let's see how we can implement that. Now is let's go to our bind-slave form, and let me use that as the base to change name first. So that is the 3, 2. So now we will have this Sierpinski triangle. Sierpinski is our mathematician in Poland. So we use this name to memorize him. So let's start to see here is our target is draw. Let's try to remember how to type on that. And if we back to the here, so I also put a link for these triangles in the Wikipedia. So here you can see here evolution of this Sierpinski triangle. First is just one triangle and go to 3, then go to 9, then go to 27. So keep adding. So it's from this wiki you can see the animation. So let's also put this as our reference link here to replace. Now is the wiki page, and we still here. So let's see. So we need to replace the rules. We only have 3 rules, so we can delete number 4. So here we only have 3 rules first. So let's ensure is we have our rules correctly put. So again is we sent the p, so x is the p 0, y is p 1, and then we pack this coordinate. So for transformation 1, so let's see the next x is the half of the current x. So that's x, and the next y is the half times y. The assumption is all these 3 rules are occurred evenly, so that is equally probability. So then we can confidently just putting those. So 0.5 times x plus 0.5. And then here, oh, it's her hard coding 0.5. So let's see, so 0.5 times y plus 0.5. And the third rule is the 0.5 times x plus 1. And this doesn't plus y. So now we have our these 3. So if I just run that, now we enter the number, so we didn't change anything. So you can see here is you already have something drawn, but it's not our form anymore. So, but how we can make the drawing is we need to use those triangle to make that. So let's also draw this. We call here is not draw form. So it's first is let's rename that is Sierpinski. And we will have this also draw Sierpinski. So and then this we ask for n. That is also the correct. And then the xy sent to the draws. We send the p to the this Sierpinski and also send n. And then this we plot is xy, so we use this O, and then here is let's see Sierpinski. How I can remember that is this can be still same. Now the difference, let's see what we can have is we send this xy. And we put this xy is 0, 0, so that is defined here. And then p is transform the p, so we have this transform and append to append and then return xy. So this draw Sierpinski is no change. And the change is possible is coming from here is the transformation is the transformation here, and probability is just the same. So 1, 3, 1, 3, 1, 3. So we can reuse. So we have this non-uniform probability, but we define that as the equally. Then we get the index and then reuse this t index. And let's say here is random. So we already have our random, and we have this C and the sum, and for P in this one, this, and we get this sum of P. So now is 1/3, 2/3, and 1. And the sum is get this 3 list, 3 item list. Then through this, and we put this back. So I think it's that's. Let's see. So if I just have 1, so I got these parts. But I think it's we should draw our the Sierpinski. So what we need to draw is let's see. So transform. What we are going to draw. So plot this. Let me see here. So run this more times. 100. Oh, you can see here is getting a little, looks like our triangle now. And let's give, like mentioned, 10,000. Yeah, so that is getting this. We are not even using our polygon. We just use the distribution of the points, and then this coming to this triangle. So if I zoom here, so you can see it's not fully filled that, but if we keep adding more, so let's see, I add another 100 times. Let's wait a little bit. Yeah, it's getting quite huge. So, and if I zoom, then it should be quite even. So you can see here is still like this Sierpinski's and keep zooming. Now it is getting the distributed. So you can see here, but if we make that the smaller, then it's almost fill the whole the spaces. Now is with 100, with 1 million the points. It's quite smooth. So that is quite nice on this Sierpinski. So that is very quick because we already have our base from the four this shape, those fractals. So you can also keep such kind of the program as your base. And again, let's recap: is you need to define our initial shape and with just our point or with the initial position, and you need to define the the repeating times or the iteration in the loop. And then the last is update your transformation rule. And if that is evenly the probability, you just now you can use this to make that is in the equal these values. If that is unequal, you can change this to the non-uniform, and we can reuse this get index and use this index to randomly choose which rules we are going to use. So this way, so we will keep using that to try to solve more the fractals, the challenge questions. So see you in the next one. Is exploring the Heinong's function. So let's also try to see how our fractal the knowledge can do those for us. So see you. Bye for now.